Hi, in this video, I'm going to solve this question that you see on the board. Find a value of x satisfying this equation. 5 times root of 1 minus x plus root of 1 plus x is equal to 6x plus 8 times root of 1 minus x square. So, looks like a complicated equation, and a solution path may not immediately jump out to you. And in fact, if you try doing your normal algebraic manipulations, like if you square both sides, or if you try rearranging the equation and then squaring it, that won't get you very far, and you should pause the video and do give that a try before you see how I solve it. So what we will do is we'll carefully observe the structure of the expressions here. So if you see here, you have root of 1 minus x, you have root of 1 plus x, and then you also have root of 1 minus x square. So this should give a hint to you that there is a certain substitution that's possible here that will make our jobs a lot simpler. And if that does not immediately jump out to you, once again pause the video and think about it. But the substitution that's possible here is a trigonometric substitution. So if you remember that 1 minus cos 2 theta, 1 plus cos 2 theta, we have formulas, standard formulas for these that then point us in the right direction about what to do here. So what we will do here is we will substitute x equal to cos theta. And what that does is, then if I have 1 minus x, so 1 minus x, which is 1 minus cos theta, will become 2 sine square theta by 2, and 1 plus x, which is 1 plus cos theta, will become 2 cos square theta by 2, and then I also have 1 minus x square here. So 1 minus x square will become 1 minus cos square theta, which is simply sine square theta. And you see that we've managed to convert all these expressions into perfect squares, into square terms, with this substitution x equal to cos theta. Okay, so let's do that. So what we get then is 5 times root of 1 minus x, which is root of this term, which will become root 2 times sine theta by 2, and then you have root of 1 plus x, so which will be the root of this term. So root 2 cos theta by 2 is equal to 6x, which is 6 cos theta plus 8 times root of this thing, which is root of sine square or sine theta. So we get 8 sine theta. And if I now take out this root 2 common, take it out of the bracket, so I get 5 root 2 times sine theta by 2 plus cos theta by 2 is equal to 6 cos theta plus 8 sine theta. And now this is the equation that we have to solve. So we have managed to simplify our original algebraic equation into a somewhat simpler trigonometric equation. But what do we do now? How do we proceed from here? Well, for that, what we need to think about is, what do we do about these expressions? Sine theta by 2 plus cos theta by 2, and here we have 6 cos theta plus 8 sine theta. Both of these expressions are what we call linear combinations. So this expression, for example, is a linear combination of sine theta and cos theta. You have something into sine theta plus something into cos theta. This expression is also a linear combination of sine theta by 2 and cos theta by 2. You have 1 into sine theta by 2 plus 1 into cos theta by 2. So these types of expressions are called linear combinations. So what we'll do is we'll take a little bit of detour, and I'll show you how to manage and simplify linear combinations of trigonometric terms. Alright, so if we have a linear combination of sine theta and cos theta, something like a sine theta plus b cos theta, what I want to talk about is how do we combine these two terms into a single trigonometric term. That is what I'm really trying to show you here. How do we combine these two terms into a single trigonometric term? So there's a trick to do that. What we do is, we have these coefficients a and b, we square and add them, so a square plus b square, and take the square root, so root of a square plus b square, and we divide both coefficients by this term. So a divided by root of a square plus b square, and b divided by root of a square plus b square, and then we also multiply this whole thing by root of a square plus b square, so that our original expression remains unchanged. Now, why did we do this? Well, what this allows us to do is it allows us to claim that there is a certain angle, let's call it alpha, there is a certain angle alpha such that the sine of alpha is this term and the cos of alpha is this term. So, the sine of a certain angle alpha is b by root a square plus b square, and the cos of that angle is a by root of a square plus b square. Now, why are we doing this? We are doing this because this allows us to rewrite this expression as sine theta into cos alpha plus cos theta into sine alpha, which we can then combine into a single trigonometric term sine of theta plus alpha. But why is that possible? Why are we able to claim that there is a certain angle alpha that will satisfy this? Well, it's simply because firstly both of these expressions are less than 1, and secondly their squares will add up to 1, which is what we want sine and cos to satisfy. Sine square alpha plus cos square alpha must be equal to 1, and these two expressions satisfy that constraint. So, there must be a certain angle alpha for which sine of alpha is this value and cos of alpha is this value, okay? And then that means that we can write this whole thing as root of a square plus b square times sine theta into this ratio here, which is cos alpha. So, sine theta cos alpha plus cos theta into this thing, this expression which is sine alpha. So, cos theta sine alpha, and now we can see that this thing is nothing but the expanded form of sine of theta plus alpha. So, what we get here is root a square plus b square times sine of theta plus alpha. So, what we have done therefore is the original linear combination a sine theta plus b cos theta, we managed to compress it and rewrite it as a single trigonometric term in this expression. So, that is what we are now going to use back in our original problem. Okay, so here is where we were. We had this linear combination sine theta by 2 plus cos theta by 2, which we can think of as 1 times sine theta by 2 plus 1 times cos theta by 2, and then we have 6 cos theta plus 8 sine theta. So, we will use what we just learnt and rewrite both these linear combinations as single trigonometric terms. So, how do we do that? Well, the square of 1 and the square of 1 when added together is 2. So, we divide both of these by root 2 like this, but also multiply the whole expression by root 2. And here we have 6 and 8. So, 6 square is 36, 8 square is 64, the sum is 100, the square root is 10. So, we divide by 10, both of these terms by 10, but we also multiply by 10 so that our expression remains unchanged. And now, how can we combine this linear combination? We need to think of a certain angle alpha such that cos of alpha is 1 by root 2 and sine of alpha is 1 by root 2. So, that angle is simply 45 degrees or pi by 4. So, this expression can simply be written as sine of theta by 2 plus that angle alpha, which is pi by 4, like this. And what do we have as the coefficient outside? So, 5 root 2 times root 2, which is 10. So, the left side then simply becomes 10 times sine of theta by 2 plus pi by 4. What does the right side become? So, we have 10 times. So, we need to think of a certain angle, let us call it phi, such that cos phi is this angle and is this value. So, cos phi is 8 by 10 and sine phi is 6 by 10. So, sine phi is 6 by 10. Okay, and then for that angle phi is, we can just simply rewrite this expression as sine of theta plus phi. Okay, all right, that's amazing, because now on both sides these 10 will cancel out, and now we finally have sine of something is equal to sine of something. So, we can simply just equate the arguments now, and that will give us at least one solution. So, this tells us that theta by 2 plus pi by 4 is equal to or can be equal to theta plus phi. And if I now multiply by 2 on both sides, I get theta plus pi by 2 is equal to 2 theta plus 2 phi, or theta is equal to, so I take this theta here to the right side, so I get theta, and this will be equal to pi by 2 minus 2 phi. Okay, that's amazing, because my original substitution, if we go back to what we had substituted x for, x was cos theta, and now I know that theta is pi by 2 minus 2 phi. So from here I can simply calculate x by using this equation that we got, this equality that we got. Theta is pi by 2 minus 2 phi. So this means that x, which is cos of theta, or the cos of this expression, will be equal to the cos of pi by 2 minus 2 phi, which will be sine of 2 phi. And what is the sine of 2 phi? It will be 2 times sine phi times cos phi. But what was phi? What was this angle phi? Remember that we assumed the angle phi to be an angle such that sine of phi is 6 by 10 and cos of phi is 8 by 10. So we know these two values, so we can simply substitute them here. So sine of phi is 6 by 10, which is 3 by 5, and cos of phi is 8 by 10, which is 4 by 5. So we have 2 times 3 by 5 times 4 by 5, which is equal to 24 by 25. So we get one value of x as 24 by 25, and we have effectively solved the question. So let's quickly take a recap, do a recap of what we did. So we had this original equation, looked very complicated. If we had tried rearranging it and squaring it, it would not have taken us very far, but instead we were smart and we said, let's do this trigonometric substitution, x equal to cos theta, because we know these formulas. 1 minus cos theta is 2 sin square theta by 2, 1 plus cos theta is 2 cos square theta by 2, 1 minus cos square theta is sin square theta. So we do this substitution and we get a trigonometric equation, and then we use the linear combination of sine and cos to combine them into single trigonometric terms like this, and from where we could equate the arguments to get a value for theta, in terms of a constant angle, and then the value of x, which was the original variable, was simply cos of theta, and which we found to be 24 by 25. So that concludes our solution. Now one thing I like to call out is, if you go back to the original question, you will see that it says find a value of x, find a value of x. So this is one possible value of x that satisfies this equation. Now the question I want to leave you with is, are there other values of x that satisfy this equation? So that's one. And secondly, if you know of any other approach to solving this question that may not require a trigonometric substitution, it may be some different approach, please do let us know and do share your own approach in the comments. But I hope you enjoyed this solution, and thank you for watching.